This is Unit 3, Section 3.7. We're going to continue looking at the normal distribution, Day 2. All right, so as we are completing this unit, we've kind of used our density curves and our z-scores to build the empirical rule for approximately normal distributions. And then we practice with our calculator being able to find that distribution, finding the proportions of the distribution, or being able to find the z-score or the observation given a percent or an area. And so we're going to continue that again today, and then we'll review and test. All right, so we're going to dive right in, practicing a little bit more of what we did yesterday. So suppose that Clayton Kershaw of the Los Angeles Dodgers throws his fastball with a mean velocity of 94 miles per hour and a standard deviation of 2 miles per hour, and that the distribution of his fastballs can be modeled by a normal, woohoo, oh, that was a bad eyeball, let me try again, woohoo, normal distribution. About what proportion of his fastballs will travel at least 100 miles per hour? So if I have at least 100, it means greater than or equal to 100. So I'm going to go to normal CDF, and I'm going to say from 100 to infinity, centered at our average here, 94, and our standard deviation here, 2. Make sure that we're labeling our lower bound, upper bound, mu, and sigma here, so that we're not just giving it calculator speak, we're saying what we know this is represented by. Then we can go to our calculator. So this is under our distribution menu. Option 2, we're going to go 100 to infinity. So I'm going to use that 1E99. And this isn't a standard normal. It's centered at, 94 with a standard deviation of 2. And we'll paste that in. And we get a standard deviation, we get a percent of 0.001. So percent would be 0.1. All right, so when we look at this, we are now saying that he has almost, not even quite 1%, hardly a percent of his fastballs will travel 100 miles per hour or more. So if we look at number 2, it says what proportion of his fastballs will travel greater than 100 miles per hour. So if I look at this, how is that different from what we did before? Okay, so this is the difference between our continuous variables and what we're going to look at when we have non-continuous or discrete variables. But right now, this would be like a solid line, and this would be a dashed line. If we were thinking kind of algebraically, we would have a boundary that's included, where we would have a bracket here and a parenthesis here. And so as we consider these things different in algebra, this is going to be the exact same thing. There's so little included here. In fact, there is no area in addition to having a line versus a dashed line. There's no additional area included. So this will be the same 0.013, same as this part A here. And it's because there's no difference here. As we continue looking at different distributions, we will have ones where greater than or equal to and greater than are different. But when we have these continuous normal distributions, those have the same answer here. On part C, when we have about what proportion of his fastballs will travel less than 90 miles per hour. So now we're just going less than 90. And so this will be our normal CDF. Now we're going from negative infinity up to 90 because we want all the observations less than 90. Still centered at 94 with a standard deviation of 2. And I'm not going to lose my points. I'm going to make sure that I label my answers. All right, so into my calculator, I will find this value. So I'll pull that up. and go negative 1E99. And then I'm going to 90. So this is less than average, so I know it's less than 50%. And to there. So looking at those numbers, I can see that it is an empirical rule one too, because 94 minus 2, I mean, I can get to that 90 observation using standard deviations. So it should be about our 2.5 that we were expecting on empirical rule, which is why we get something pretty close to that. All right, on the next part. About what proportion of his fastballs will travel between 93 and 95? All right, so now we're saying what proportion of his fastballs, 93 as our lower value, and then we have our observations between that and 95. So normal CDF, we're looking for a proportion, 93 lower, 95 upper, still an average of 94, and standard deviation of 2. Lower bound, upper bound, mean, and standard deviation. All right, to our calculator. I always think of it as like saying to the back cave. So in our distribution, we'll choose option 2 again, now going from 93 to 95, still have that same standard deviation and mean, and when we calculate it, now we have 38.3 here. And so as we keep looking, this calculation is helping us find if we had a distribution centered at 94 going by 2s. So when we look at this 93 to 95, it's this data, which is why it's quite a bit of the data there. It's right at the center of our distribution, and it should be a considerable amount, because if we go all the way down to here where we're at 92 and 96, that would be our 68%, capturing it using the empirical rule. On the next part, it says, what is the 30th percentile of Kershaw's distribution of fastball velocities? So this is bringing back in our 3.1 section. And so in that section, we define percentiles to be equal to or less than. So we're trying to find the observation that would give us the 30th percentile. And so we need to find that observation. This is going to be an inverse norm problem. We know the area we want is 30th percentile, and we have the average, 94 still. We have the standard deviation, 2. So now we have area, and Beyonce's happy because percentiles are to the left, so whatever we have to the left is 30% of this observation. We don't know what it is. Still centered at 94 with a standard deviation of 2. So when I put this now in my calculator, I can go second distribution, option 3. I have an area of 0.3. Make sure that you're putting that in as our percent. And it's not standardized. We're at 94 and 2. And so now we know that his 30th percentile, so 30% of his observations or less, go 92.95 miles per hour. And on the last part, it says, what fastball velocities would be considered low outliers for Kershaw? All right, so if we were thinking of low outliers, there's a couple ways that we could do this. We have our 1.5 IQR rule, and that would say our lower bound is quartile 1 minus 1.5 quartile or interquartile range. And so this is how we would identify those low outliers. We could also use 3 standard deviations below would also be our outliers. And so as I'm given the information, I know the mean is 94. I know the standard deviation is 2. I'm just going to use this rule and check for what would be considered a low outlier, something that's significantly different than what would be his typical fastball velocity. So if I take 94 and minus 3 of the standard deviations, I'm at 88 miles per hour. And so because of that, we would have this outlier. Anything that is 88 miles per hour or slower would be significantly different for Kershaw. All right, and then this last part, it says, suppose that a different pitcher's fastballs have a mean velocity of 92. All right, so we have a mean here of 92, and that we know 40% of his fastballs go less than 90 miles per hour. Okay, so we know that the proportion of his fastballs that go less than 90 miles per hour is 40%. What is his standard deviation of his fastball velocities? So this is similar to where we're now connecting this idea of there's a normal distribution, because they're saying that assuming his distribution can be modeled by a normal distribution, woohoo! So we have this now centered at 92, but we don't know what the standard deviation is. We do know from here that 40%, here's 2.5, there's 16, and almost all the way to the middle would be 50. But what we don't know, we do know that this is at 90, but we don't know how far away that is here. And so one of the things that we want to do is connect it to the standardized distribution, where we always know the mean and the standard deviation. That comes from standardizing every score, taking every observation, subtracting the mean, and dividing by the standard deviation. This is how we can relate the true data with the standardized data. So we already have this idea of, okay, we know the observation, that's our 90. We know the mean, that's our 92. What we're missing is the standard deviation. So we need to find the standardized score of what this would be represented here. If I standardize to 0, and now I know standardized would be 1 standard deviation. And so there's got to be a matching piece here that would represent that 40%. And so just like we have the 40% here, we would want to have some Z standardized score here. I can use inverse norm here because now I have that 40% to the left, Beyonce's happy, and I know both parts here. I can't do it on this one to find what the standard deviation is because when I try to use the 92, I don't know what that standard deviation is. So that's why we have to standardize it to find this Z-score here. And so when I put this in my calculator, we're going to go inverse norm, 40%, and then we're going to standardize this. So 0 and 1 is our standardized normal curve. Gives us a Z-score of 0.2533. All right. Now I can solve this for our unknown standard deviation. So now I have 0.2533 equals -2 on the numerator. And then I can multiply by standard deviation. It gets rid of it on this side. But I need to undo that multiplication here. So I'll divide it, giving me 0.2533 on the bottom. And I can use my calculator to find what that standard deviation is. -2 divided by 0.2533. So I get -7.89. All right, one thing to consider is that the reason that we have a negative standard deviation is because we are going below with our observation. So we had a negative value here. So when we report the standard deviation overall, we would say it's that positive 7.89. If you said negative, that's okay, but typically when we find standard deviation, it should be a positive. In this case, we just got the negative because our observation was lower than the mean. A lot of this is similar to the problems and the samples that we did yesterday or last time, but but I want to make sure that we're re-emphasizing how to use our calculator and how the standard normal is related to the observational normal. And so one of the things that we have to be careful about, though, is that it's not safe to assume that all distributions are normal. Just because we have a symmetric graph doesn't mean it's normal. And so one of the things that we want to do is check for normalcy. And so there's two ways that we can do that. And so on the first one, we have our example, and it says the following are the unemployment percentage rates in each of the 50 states in November of 2009. All right, so here's all 50 states in 2009. Below is the histogram of the data. Does it appear to be normal? How do we know? And so does it appear? Yes. I mean, we kind of have this nice curve here that's coming through. It looks like there's less on the tails, that we definitely have this kind of center here. And so how do we know it appears to be normal? We would say because it is roughly symmetric. Another reason we could say is that it is bell-shaped. As we lay that density curve over it, takes on that bell curve, and there's a single peak. So just by taking the data here and putting it into the histogram, we're starting to see this kind of take on a normal shape. But how do we actually know? When we go here and say, okay, given the mean, so now they're finding that mean for us, and standard deviation, check to see if it fits the 68, 95, 99.7 rule. So if it fits about here, this is how we would know it's normal. If it's not pretty close to this, it's likely to be roughly symmetric or roughly or approximately normal, but it wouldn't be exactly normal. And typically, most data sets are going to be approximately normal. If it's far from our empirical rule of 68, 95, 99.7, then we would say that it is not normal. We would just go back to saying it's symmetric. And so when we find these values, we're going to take our average and add and subtract one standard deviation. And so I've calculated those. I get 6.457 going down 1. I get 4.232 going down 2, and I get 2.007 going down 3. Going up 1, I get 10.907. Going up 2, I get 13.132. And third time, I get 15.357. So when I look to see how many of my data points are captured between one standard deviation, so 6.4, and it's nice that this data is in order for us here. If we look at 6.4, that would be from here and then up to 10.97. So we'd go all the way, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Oh my gosh, I'm not all the way there. I need to go to 10.9 here. So all the way to here would be captured. It's almost easier to go backwards and say, okay, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 are not included here. And so as we look at that from 6.4, wouldn't be included, so let me move my thing here. That's too little, so I'm going to go up to here, which gives me 14 that are not included, so that gives me my 36 here. So approximately that would be 72% if I did the division there. Okay, if I move mine now looking at 2 standard deviations, 4.2, okay, so now I'm down here up to 13.1 up to here. So now that's including everything but 2. So that's going to be 48 of my observations, giving me 96% here. And then my last one, if I go from 2 points, well, that's everything down here, up to 15 points, that's 100% of my data. That is all 50. And so as I look at this, how do I tell? Is this pretty close, 72, 96, 100 to the empirical rule? Because this is very close, this confirms that we are seeing that it appears to be approximately normal. If I found out that this was like 40 or this was 100, okay, if I had something that was pretty far from 68, I wouldn't even need to check the other ones because I could say, nope, that's way too far. Or if I had significant outliers. So if I went 3 standard deviations and I still wasn't really capturing the entire observations, then I would say it's probably not fitting our normal distribution because we need to have no outliers as well. So another way that we can check for normal is a normal probability plot. And so this idea arranges the observations from smallest to largest and then finds the percentile of each. Then it plots the observations against the expected z-scores, and that's from our table A or our calculator for those same percentiles. If the data is close to normal, the points will appear to lie along a straight line. Okay? So given is the normal probability plot for the unemployment data that we had above. Does it appear to be normal? So it's asking, if we looked at this, does it appear to have a linear form? And so again, this is where we would say, yes, it does take on. It has some variation in it, but the points lay very closely to a straight line. And again, this is another way that we would confirm the normal distribution. And so in the end, when we have very close to the 68, 95, 99, 7 rule, we have a linear normal plot here. Is it safe to assume that this distribution is close to normal? Yes. And so we can confirm that because the histogram looks fairly normal. So here's kind of what we checked. And so when we say it appears normal, it has that single peak, bell shape, roughly symmetric idea. It's close to the empirical rule. And then we would say the normal probability plot appears linear. So while I've never seen any test question, whether it was College Now or AP, that required us to actually create a normal probability plot, I have seen them provide the data in a plot like this and said, all right, is it safe to say that it appears normal? I've seen graphs where they had ones that looked like this. Okay, if this was the normal plot, this is not taking on a straight line. This has too much variation to say that this would be an approximately normal distribution. It's too far off from that linear expectation that we have if we have a normal distribution. Even the couple of differences that we have here are not far from that linear pattern. And so if we looked at the histogram one more time here, we do have some concerns. We have a gap, we have a lower value here. We would want those to switch, but that's not going to give us such a huge concern as having a normal probability plot that looks like this, or maybe even something that would be, almost quadratic looking. Okay, we can't fit a line to that and have it look pretty good. So the AP tip there says if we don't know it's perfect, we're always going to say it's approximately normal. And so unless they say this is a normal distribution, then we just assume that it's approximately normal. It is close to the empirical rule. It appears to be normal. So we use these kind of vague words that help us say it's close to, it appears to be, but without saying it is this. And so that's kind of how we would check our data. If you have any questions on this or how to use your calculator, let me know.